took the time to talk to me today over lunch and our presentation. Thank you for joining this presentation. Let me just say a couple of words. I'm doing maybe too many different things. I'm spreading out too much, and I have to select what I'm doing. So what I'm doing roughly is I'm very interested in the convergence between biology and engineering. And because of my training, I'm interested in taking principles of adaptation from biology and translating them into things, engineering things that make sense from an engineering perspective. So not just copying for the sake of copying, but at the same time, I'm also very interested in using these artifacts, simulated and physical devices, to go back to biology and test some of the hypotheses, the biology step, for which there is no fossil record. For example, in terms of evolutionary biology, what are the conditions for the emergence of altruistic behaviors? There is no fossil record for that. What are the conditions for the emergence of communication? There is no fossil record for that. Or there are some situations, behavioral situations, where animals display some behaviors that, for which there are different explanations, but it's difficult to set up system with animals, or ethically difficult to set up systems with animals to test this hypothesis. And there are robots, which are physical systems with sensory motor properties, are a useful tool for testing some hypotheses. So that's what I'm doing. And if you look at currently at the research avenues in my lab, I'm doing essentially evolutionary robotics, which is essentially using these, co-evolving the brains and the bodies of these robots for biological purposes and for synthesizing robots. I'm doing area robotics, so biological inspired area robotics, which is what I will be covered today. Not all the projects, but some subset of those projects. I'm doing wearable robots, essentially soft biological inspired systems that you can wear and that can help you transform yourself into a non-anthropomorphic individual, which is a robot, which lives in a different space, in a different scale, and with different sensory motor capabilities. I'm very interested in morphing. So, of course, we know that the brain can adapt to different, like spectacles with inverted things, but the question is, with the help of our body exoskeletons, could we make people feel and become a different being? And that's very interesting for the avatar type of experience, where you project yourself in a machine with different. Anyway, but today, and the light motif here is biological inspiration, and most recently, soft robotics. And this will come up in my talk today. So today I will be covering biological inspired robots. Is it possible to switch these lights off so that we can better see the screen? Okay, if it's okay with you. Yeah. Oh, that's on. Maybe it's, oh, that's better.
Other side of the door. Other side of the door.
I mean, we can keep you in light. It's just the only thing. You can turn on those on the back.
Flip the bottom switch.
Yeah. Because if you keep it off, I think this is fine. Yeah, I think. Okay, so what you see on this picture is some of the things we'll be covering today. This is an artistic rendering of where I want to go. And what you see is that you have flying systems. They are biological. They look like biological systems. I'm not interested in copying their shapes. I'm interested in getting inspiration from some of their properties, morphological and mechanical and sensing properties. What you see is that they are flying in dense environments, which means they must be perceptually aware of what is around them, or capable of dealing with close contacts with buildings and people. And what you also see is that you have many of those. And so these are the three things that I'm interested in. Now, when I'm talking about drones, what really I mean by drones is small systems, which, okay, that's great. Let's see if it doesn't move. Okay, we're talking about small drones, and by small we mean less than a kilogram. These are the canonical shapes of those drones. You've got flapping wings, you've got multicopter structures that can hover, and then you've got fixed wings. So then you have all sorts of different combinations, but essentially, by small I mean less than a kilogram mass, so 2 pounds. And when you look at these drones, you're saying, well, what type of drone is good for what? And I was spending some time in the sabbatical at the Rob Woods lab in Harvard a few years ago, and we looked at, we decided to map out the capabilities in terms of flight autonomy. That means for how long these different platforms would fly, and against the mass of these vehicles. And what you see, this is logarithmic scale on both axes. We are plotting different types of drones, floating wing, rotorcraft, fixed wing, And there is an interesting trend. The first thing is that there is a linear trend, no matter what you're looking at. But if you're interested in platforms that can cover the longest distance for the given mass, then you definitely want to go for fixed wings. You see the blue circles up there. Today, this is still valid 3 years later, definitely, and it scales up a little bit further than a kilogram mass. If you want to have more agility than a fixed-wing drone because you want to stay in place and do rapid maneuvers, then you need to go down to the rotorcraft multicopters, the triangular green shapes. And if you want to have even more agility, you want to go with flapping wings. Flapping wings can do amazing agility, but the problem with flapping wings is that they tend to have lower autonomy. Though, if you want to scale the system down, flapping systems are much better. So we could discuss a lot about these things, but that gives you a rough idea of where these systems, how these systems compare. Now, with these drones, we could do a number of different things. In rescue situations, we could have drones up in the air can stay for a long period of time with fixed wings and establish radio communication, adopt network in situations where the typical communication infrastructure is no longer existing. That fly into buildings to look for people. We could have transportation delivery drones that take emergency kits to the location. We could have small drones that can fly into areas where no other type of robot could potentially go. So how do we go there? I will try to show to you some ideas projects that go towards this general big picture. When I started off doing drones, that was back 2005 or 2006, we were essentially building fixed-wing platforms like this. And the Swiss Army contacted me and said, look, in Switzerland, we have a lot of landslides and situations where we have isolated villages in the Alps after landslides, and the communication infrastructure doesn't work anymore. Before we send rescuers on the ground, we must set up in place a communication infrastructure by dispatching trucks at strategic locations, and only when we have that communication infrastructure in place, then we send the rescuers down to the ground. And that takes a long time. It can take hours to get in place. And they asked me, could you develop drones that have emitters and receivers on the wings? They can be simply deployed out of the box by a rescuer. They would go out. They would map out the entire area and distribute themselves so that they establish an ad hoc local network that picks up the signals from the rescuers on the ground, creates a bridge on the sky, and connects the drones immediately. And they keep flying by simply following the signals. And they said, if you possibly can solve this problem without GPS, that's great. Of course, the Swiss Army, also in case of defense situation, the GPS signal probably is one of the things you cannot count on. And that was a difficult part, because you say, okay, how do you do that? And so, to make a long story short, we used an evolutionary algorithm to evolve a very simple neural network that looks at the magnetic compass that these drones have, and looks at the strength of the signal, and they look at the timing. They have like a time dimension. They look at the time of the signal detected by these drones when they move out and in. And so this evolutionary algorithm came up with a solution that we then translated into a simple program that allowed us to connect two people on the ground. So here you see one of the simulated rescuer, one of my students, and there is another student down in the forest, downhill, a few kilometers apart. He's launching the drones. The drones are flying out. They're spreading out using simply the strength of the signal. They're searching for the other person. And so what they do is that they move out, then they start to spread out, and they cover a large area until they pick a signal from a person, and then they line up precisely so that they establish a bridge. Sorry for you can't see the drones precisely moving up in the sky. But essentially, this worked very well. Now we are scaling this up to multiple people on the ground, especially teams of people who are moving in cities where you've got these canyons, so the signals is very restricted. So you have, for example, an earthquake or a situation where you want to send police very quickly in, or rescue teams, and they have to communicate as they move around these environments with all these drones following them and distributed themselves. So that's one area of research. We have also been looking into sound. Oh, there is no sound. That's a pity. So why don't we have sound? So this is connected. This is connected, and that's a little bit of a problem. Let me let me just see if I can get the sound. 1 second, because there is a lot of stuff that has sound. So system preferences, sound, headphone port. Yes, it's in here. Should be okay. So something happened, right? Okay, let's try again. And so okay, let's see. Okay, this is not working. This is off. Is it because the power is off?
Safety whistles are often carried and used by people engaging in outdoor activities such as hikers, mountaineers, skiers, porters.
Anyway, essentially, let me. And now we don't have video. How comes? What? Why? Okay. Now even the slide is disappeared. Is it maybe there is a contact in this? See, the plug is loose, so definitely because the signal is out here. Yeah. So there is no more output from my computer. Projector is on, but it's red light. There is a red light. Excuse me. Yeah. No. I think projector is dead. Yeah. Yeah. Or is at least off.
Why does this blinking? Dario, this has never happened. It's not working?
No, the projector is
Is it?
I don't know.
Okay. I hope it's not all. Yes, control. What control? Control of this. There is a control from here.
Oh, so that's, yeah. So now we just gotta wait. Yeah, just gotta wait for that.
The speaker is working either? No, the speaker was not working. It wasn't working. Because I heard that basically the speaker was working because there was a so I used to need to get through someone else to put it together.
Well,
But we don't even have a picture. Huh? Yeah, that is one thing, but the speaker isn't right now. We could say that before.
yeah, this is what you have to take together. Well, you get an intermittent connection. Now it's off.
Yeah, you're gonna have to we're gonna have to hold it together. Okay, now it's not blinking anymore.
oh, it's green. Now we see green light there. That's good.
I don't know why it went off before.
Maybe there was a contact in this cable.
No, this cable is for the speaker.
It's just for the speaker.
So
Yeah.
we hold this just to make sure that the screen stays on. The speaker's a different. Oh, it went off. Projector is coming back on.
Okay.
Here, I'll be that.
Yeah, you sit there, Jeff, and hold it. This is why we need to make everything wireless. That's why next time we needed it beforehand. You could. Are you ready to just verbally talk about it?
Yeah. Okay. I think it's okay. I think I won't start.
Back on.
Okay.
Back on.
Fine.
You need to deploy a drone system there.
Just stay around for a few minutes. I can't see that one because there's no one. Just stay for 5 minutes.
Okay. So maybe we skipped it. What I want to say Yeah, okay. So what I want to say is that essentially you can use radio signals, but you can also use the put microphones on drones, and you can listen to two things. You can listen to sounds, emergency sounds from the whistles that people use in emergency situations, and you can use the GPS on the drones to tell the position of the person. So essentially, the drone has microphones, flies out. There is a person who is lost somewhere in the forest. The person uses the whistle, and as the drone flies with the microphones, it can detect where the filter optimization to process the signals coming from 3 microphones and locate the person. So the drone would fly over the source of the sound, and with the GPS, we would know exactly where the person is. So that's a very powerful solution. Then it turns out we can also have swarms of drones that know each other, how far they are, and the range and bearing by listening to each other. And at the beginning, I thought it was impossible because of all this noise that drones make, but it turns out that if you have fixed wings, it's very easy. You can temporarily switch off the engine of the listening drone to listen to the other drones. And you can even modulate the rotation of the motor speed of the other drones to give a specific signature to the frequency, so that not only the drones know the range and bearing of the other drones, but they also know which identity, which drone is what. So that's very interesting. If you have quadcopter, you cannot temporarily switch off the propellers because that would destabilize the machine. So in that case, we put a beeper, very loud beeper on each drone, and at a particular frequency that's not covered by the frequency of the wind and of the rotors, and you can do swarming localization by simply listening to the other drones. So it's quite an interesting thing without using additional type of sensor ports. But now vision. The vision is extremely interesting source of information, and we know that insects use it for a variety of different things: attitude stabilization, collision avoidance, homing, attitude regulation, chasing, swarming, all sorts of things. And it's very lightweight, so it's a passive energy, it's a passive sensing device. And we know now for many years that essentially what insects do is that they are sensitive to optic flow, which is this pattern of variation of the features as the insect flies through the environment. And we know that as long as the insect flies in a translational the trajectory, then the magnitude of those translations of the optic flow is proportional to time to collision, or you may call it distance if you know your own speed. So a number of models have existed in a number of neurophysiological findings have been done. For example, we know that, for example, in the Drosophila or in the flies, there are a number of neurons that collect information in the brain of these insects from multiple photoreceptors on the compound eyes of the insects, and each of these neurons is specific to a particular pattern of optic flow in the eye, which is then, after only 2 synaptic connections, translates into a pattern of motion of the insect. So it's a very nice machine. We have, for example, in Drosophila, approximately 13 type of neurons which are sitting in a particular part of the brain called the lobula plata, and we know exactly where the receptive fields is. You can make an automaton, a machine that would react to different patterns of optic flow, like landing, taking off, collision avoidance. We said, okay, could we simplify it and have only 2 neurons, 2 of these neurons? Imagine that you have a fixed wing platform like the one you've seen here, and this fixed wing platform essentially controls the trajectory by pitching down and up and then rolling motion. And the combination of these 2 control systems gives us all the nice control of the machine. So essentially we decided to have, you don't see it in this so well here, unfortunately, but we have 2 kernels or 2 neurons. One neuron that is sensitive to the optic flow coming from the ventral side of the machine, which is connected to a positive gain. So essentially, whenever the optic flow increases in magnitude, the platform will pitch up. And then we have another kernel, which is looking at the optic flow coming from the left and the right side, and depending on where there is more magnitude, it would roll on one side or it would roll on the other side. Now we can generalize that. We can imagine that we have a camera looking forward, and now we simply generalize that we imagine that you have a camera, you take information on optic flow from different areas of your camera, which you see over there, and then you connect all the pixels that look at the ventral side positive gains, and there is a shape, it's a Gaussian shape there in the weight. And then you have negative weight coming from the top, in case you want to fly under bridges, for example, you want to pitch down, then pitch up to avoid obstacles on the ground. And then we can do the same generalization for the other kernel. We have another neuron that is now the same thing. We extend it to the negative weights on the one side and positive on the other ones, and that's all we have. So 2 neurons that pull together all this information, and then we know that depending on where you look in polar coordinates at the pixel of the camera, we have 2 parameters we just have to adjust. We have a simple formula. You do that, any type of geometry you have, you can use these 2 kernels. So imagine that you have a vision system in a fixed wing platform. We are looking at the top of a fixed wing, and we have multiple cameras. Each of these cameras is pointing in different directions. You see this camera is pointing in the ventral side. As you move sideways, you're pointing slightly up. And each of these cameras has a motion detector that comes from one of these optical mouse devices. We made the lenses so that they focus a certain distance. And then we have these 2 neurons. It's like 2 lines of C code, essentially, that pull together information about the intensity of the optic flow. And we use this to control the pitch and the roll angle of the platform. We launch this platform in the air, and you see it's capable of not only avoiding obstacles, but it also goes up, and then it automatically goes down, and then it will avoid the ground, essentially doing altitude control. So 2 neurons, you do altitude control, obstacle avoidance. Extremely simple. So we did all this stuff, and then at some point we knew how to control multiple drones, how to add this vision-based stabilization. We created the first company, Reza mentioned, called SenseFly, that back in 2009 started to sell platforms like the one you see on the right for imaging purposes. So the machine that was extremely simple to control, you launch it in the air. It's capable of doing all the altitude regulation. People don't need to control it remotely. And then the company developed a new platform, quadcopter, and then we sold the company to Parrot a couple of years ago. It became the 2nd largest producer of professional drones in the world. First one being DJI in China. But the beautiful thing about the research project that I've shown to you before comes here. So that drone you have seen that doesn't have vision-based capabilities to avoid collisions, but we added few sensors, optic flow sensors, on the ventral side, because one of the difficult problems is that landing these platforms, when they've done their mapping, they have to come back to the operator. Typical operator would be a farmer, would be somebody who is operating a mining company, and they use this for looking, mapping stuff. When you have to bring the drone back, you have to land it, you have to take over control of these drones. That's very difficult. So you could use GPS, but GPS is very bad if you look at for the vertical, for the altitudes. It's okay for the X and Y coordinates, but when you look at the Z coordinates, the error is like 10, 20 meters for commercial drones, for commercial GPS. So what we did is that when the mission is completed, the drone comes back to where the operator is down here, and then starts decreasing the altitude. When it reaches approximately 50 meters, flies back approximately 150 meters, and then it starts the landing procedure towards the operator completely autonomously using GPS. As soon as it reaches 25 meters altitude from the ground, it switches on the optic flow detector on the ground, and it fuses it with the GPS, and it does a very graceful landing so that we can guarantee landing within 5 meters maximum of the operator without any control from the operator. So it's a small translation of big research, or a lot of research into a small thing, but it's very useful. But if you look at that camera, that optic flow camera, was not very, it was a bit bulky. So how could we have compound eyes like those of insects that are so small, compact in space, and give you so high resolution? So I set out to do a European project where I brought together people with different skills in optics, and neuromorphic chips, and we built a compound, artificial compound eye, which is composed of 3 layers of materials, which are manufactured first on the planar surface because we wanted to make it a product. So we use traditional planar manufacturing procedures. We have 1 layer of polymer lenses that you see there on top. Then we have 1 layer of neuromorphic chips, analog VLSI chips that you see in blue here. Each of these neuromorphic chips mimics the properties of the housefly receptor, so they can adapt to different luminosity of the environment, and they are sensitive to contrast, to the motion in contrast. Then we have a flexible printed circuit board that takes all the signals out of these photoreceptors. And each lens is precisely aligned with each photoreceptor. We also have a number of black thin film polymers, so that essentially we make sure that we don't have crosstalk of photons coming from neighboring lenses. We make sure that each photons coming to one lens goes precisely through a tunnel, precisely on the photoreceptor here. So we align precisely the optics with the anamorphic chip with the contact points on the PCB. And then we cut columns of this planar structure down to the flexible PCB, and then we bend it around the microcontrollers or the wings, like brains, like the eyes of the insects cover the brain, computing power. And by doing that, we realized this artificial compound eye, which is larger than the compound that we have in insects, of course. But you see, if you look at the compound eye, it's essentially only this black stripe. The other is the scaffold that we built. It has 700 ommatidia, each single eye, which has with a total weight of less than a gram, a total thickness of less than a millimeter, and it has the same properties in terms of adaptation to different light intensities that the insect has. It has the same properties in detecting, precisely the same properties in detecting optic flow. It has the same type of visual field opening with no aberration coming from the sides as the insect does. Of course, it's a cylindrical compound eye, so you don't have the spherical properties of the insects have. So then, as we were working on this, a paper came up in Nature with the first demonstration of the first compound eye that we have evidence for. And the first compound eyes that we have evidence were used by trilobites living between 250 million and 500 million years ago on the floors of the oceans. And these animals had cylindrical compound eyes you don't see them, but they're sitting on the top here. They have two cylindrical compound eyes, and they have exactly the same dimension as our compound eye. So it's amazing. And so if you give us 250 million years more, I'm sure we'll get down to the size of insects. But the beautiful things about this is that you can also make vision tape, what I call vision tapes. You take the same technology, you make a line of photoreceptors on a flexible PCB. We have strain sensor, bending sensor, that our colleague Stephanie Lacour developed at EPFL. And we can bend these sensors. And with the strain sensors, we know the relative angle, visual viewing direction of all the ommatidia. And so we can do the computation and see, we can give vision to any bent object. So we can put it, for example, around the semisphere like this. And by doing that, we have 360-degree field of view everywhere. Now you say there are blind spots here. Blind spots can be easily addressed by slightly changing the viewing direction of every triplet of ommatidia so that we completely cover the 360-degree space. So in the future, this is work in progress, but we would have compound eyes that are used for obstacle avoidance, maybe glued around shapes of drones, and then we would have more traditional cameras for doing other types of operations in the center. But no matter how good your visual system is, no matter how good your control system is, if you want to fly in cluttered environments like this, taken from the Fukushima nuclear reactor disaster, sooner or later you will hit one of these cables or one of these sticks and fall to the ground. And that's a problem, because as soon as a drone falls to the ground, then typically it breaks. And so I said, okay, maybe we should think differently. We shouldn't try to make drones more intelligent in terms of avoiding obstacles. We should look at what insects do when they collide with things. And essentially, insects have two strategies, I would say they use. One is the fact that their body is not rigid, doesn't break if they fall. They have exoskeletons that can be compressed. They absorb energy and they render the energy back in the environment. This is beautiful work done by Bob Full at Berkeley, squeezing these cockroaches through presses. And the second thing, this is work done by Susan Combs when she was at Harvard. She put these wasps on, the wasp is dead, on the tip of a drill. And she rotates this drill and lets the tip of the wings of the wasp get in touch with the surface. And she noticed that these wings are extremely resilient. They resist thousands of collisions with an obstacle, and they do so because essentially they have a variable stiffness. They have lines of flexion, which normally under the type of mechanical forces the insects experience during flight, they do not bend. But as soon as there is a much larger mechanical force applied, they just give way. They bend, and then they snap back in place. And so I thought that's quite powerful. And so we designed a new type of drone which can fall on the ground without breaking, absorb the collision. And I think I'll just show to you the video, and it explains this. So it doesn't look like a wasp. It's made of an external frame and a case. So the external frame is extremely flexible. You can bend it with your hands. But like this, you don't have sufficient rigidity for flight. But okay, so the external frame is very flexible. What we do is that we put the inner body that has a microcontroller and the battery inside with magnets, and so now the structure is extremely rigid. So you see, then you can fly. So it's so rigid. Now you can fly this. And now, as you will see, it flies against the wall, it falls on the ground, and then it takes off. Now let's look at it in slow motion. You will see that the drone flies against there. It deforms, it absorbs the collisions, falls on the ground, absorbs the collision, and it doesn't break. Okay. Now let's look at it again. You see also we have small ropes that keep the inner body in shape, and then it snaps back in shape, and it doesn't break. So it's a way in which we abstract those rules, and we make a machine that is, I call it the unbreakable drone. The second strategy that the insects use is, I sent a student to Rob Wood at Harvard to measure how flies, oh, I'm so bad. So anyway, the student was measuring what happens when flies fly in very confined environments. And what we noticed is that flies don't try to avoid any more obstacles when they fly in this environment. They just collide all the time. The body absorbs the collision, and they use the legs to upright themselves in flight, or if they fall to the ground, to upright themselves in the right position from where they can take off again. That's another interesting strategy. And so I thought, okay, well, we could design drones that have a cage that can absorb the collision and retractable legs. So when they fall on the ground, when the control system cannot stabilize the drone, they would release the legs to upright themselves again and fly off. And we did indeed make a prototype here. It uses Euler spring cage. I'm sorry, don't say it so much, but it has retractable legs that upright the drone, and then the drone would fly again. So the goal of this drone is to fly towards the end of the corridor where there is light. It has only one light sensor that is rotating on the top of the drone where the red light is. And essentially it uses, thanks to its morphologies, all it tries to do is to fly towards the light, and it will collide with things, fall on the ground, take off again, and fly again. So we are trading, if you like, intelligence for morphological and mechanical properties.
The videos we'll post online come through much better.
Okay, that's great.
Those don't now, sorry.
Yeah, that's great, great. But of course, that's not a very efficient way of dealing with collisions, because what happens is that you have an obstacle, and the torque vector is destabilized, and it would point in a direction that's not the direction you want to go. The drone would fall on the ground, and then you have to use energy, a lot of energy, to take off again and fly. And so we thought, well, how could we prevent the falling? And then we thought, what we could do is that we could have a cage, an additional cage with a gimbal system that freely absorbs the collision and freely rotates around the inner cage, so that the propulsion system, which is solidar with the inner cage, remains stable, passively stable, as the outer cage absorbs the collision. So we translated that into, is the video, the sound?
The goal of this flying robot is to reproduce the amazing capabilities of insects, especially the fact that they can collide with things and continue flying afterwards. To reproduce this, we realized that we could put a lot of intelligence in the mechanics by having this rotating frame around the inner frame that always remains stable even when there are collisions. So this allows us to send the robot in a very difficult environment, for example, for search and rescue missions where there are obstacles. And we can do that without complex obstacle avoidance techniques, so that we have a very lightweight platform. The novelty of this platform is its rotating protective frame. It decouples the inner frame with all the stabilization system and avionics,
so that when a collision occurs, the inner frame remains stable and only the outer frame rotates. To test our robot, we flew it completely automatically through a forest. We just gave it a magnetic direction, and without any obstacle avoidance technique, it was able to fly for several hundred meters while encountering multiple collisions with trees.
So this drone is quite you see the camera is attached to the propulsion system and it's not much destabilized. You can cancel out the outer frame very easily. It's also safe. You can touch it, you can grab it. So it opens a range of different things. We sent this drone to the United Arab Emirates competition, Drones for Good. The goal was to locate a person in a collapsed building across the river. And out of the 800 entries from 57 countries, it was back in 2015, we were the only one who could do this. And so my students got a $1 million US award for doing this. And we said, hey, we have a great thing here, so we should start a new company, because we can go and inspect things that no other system can go. You can fly in very confined spaces. You can do inspection of boiler tanks, inspection of large industrial boilers. You can send this into caves. And so we spun off a new company called Flyability, which this is the refined version of the drone. It doesn't require very difficult. It's not difficult to pilot this drone because essentially you can.
The world's first collision-tolerant drone.
So we have improved the communication system so that you can send this down the ground hundreds of meters and do inspections where no humans can go. And so that's the company is doing very well. It's quite successful, and it's already selling for very well. Okay. Okay. So, but let's go back to our situation like this. Let's go back to Fukushima disaster. Maybe there are situations like here. You want to send drones to do sensing, for example, radioactive stuff, but you don't want to get too close to it because it's very dangerous. So you want to stay a few kilometers away. Now, if you want to do sensing, you want to go very close down to the ground. So you may want to send a quadcopter. But quadcopters, if you want to cover long distances, as you've seen from the second slide from my talk today, need to have a much larger mass than a fixed-wing drone. As in, if you have a much larger mass, much larger vehicle, then you probably cannot go into small places and do inspection. And so we said, how do animals do this? How could we have a flying wing that can also go to the ground and start locomoting and going to the location where you want? And we found, nature is amazing, we found that there is an animal, the vampire bat, which reuses its wings for jumping on the ground. And what it does, it flies near a camel in the desert, and then it jumps up to the leg of the camel, and then it sucks the blood for the camel. So we found that's very interesting because it's a sort of morphological adaptation for multi-local locomotion. Instead of having wings and a locomotion system, you just reuse the same actuation system for two different locomotion modes. So we created the first prototype here, which if you have.
The laboratory of intelligent systems, we are developing a flying platform which has the ability to move on the ground by using its wings only. A locking wing mechanism was designed to ensure a good position and rigidity of the wings during the flight phase. Once the wings are locked, several motors are used to actuate the elements on the wings which control the flight. After the robot has landed, the wings are unlocked and can therefore rotate continuously, allowing the robot to move on the ground.
So it's very stable.
Using the wings as legs to move on rough terrains, instead of adding an additional structure to the robot, allows to minimize its structural mass. Therefore, this design minimizes the total weight of the platform and thus minimizes the impact on the flight performance of the robot. The morphology of the robot is optimized for ground speed. It can move forward at 0.2 meters per second and can rotate on spots at 25 degrees per second. The robot is capable of walking in different surfaces, can overcome high obstacles, and can also navigate in rough terrains.
Yep. So just to move on. If you want to do multiple types of locomotion, we typically have different types of constraints. For example, if you look at ground and aerial locomotion, you need different values for torque and speed. So when you are in the air, you need very little torque, very high speed for the ailerons. When you are on the ground, you need a lot of torque, not very high speed. when you're flying, you want to have your center of mass slightly forward. When you're on the ground, you want to have your center of mass precisely balanced in the center of your vehicle. The inner ratio, which is essentially the distance of the tips of the wings from the center of mass of the drone. When you're flying, you want to have wings very much spread out. When you're walking, you want to have the tips of the wings closer to your body. So these are different constraints that when you want to adapt the morphology, you want to make your system, to bring your system so that you are in these different contrasting values are optimized. So, so now we looked again birds, and we see that birds, for example, like bats, they have certain type of morphologies that allow them to move those different types, especially those multimodal locomotion, to move those different properties into a regime that minimizes the cost of transportation. And we created a new platform, which is here, which is has some springiness and softness to it. So there is a system of springs and softness so that you can hit the wings and they will not break, so they can sustain hard landing. So you see here, we are with the hammer, we are hitting the drone, and it doesn't break. So anyway, I don't have time to show the video, but essentially we came up with a principle, we call it of adaptive morphology. We look at the animals that change different locomotion modes, and we see how they adapt their shape, their morphological shape, so that their muscles operate in the optimal regime. And then we extract design principles for drones, for machines that display multiple modes of locomotion. There is another type of locomotion, of morphological adaptation that birds have, and they use it not for multiple types of locomotion, but for flying in different aerodynamic conditions. So, for example, if you want to fly at very high speed in order to minimize drag, you want to have small area surface instead, but then you will have smaller maneuverability. If you want to have higher maneuverability, you want to spread out your wings. So we see that birds, indeed, as it increase, no matter what the bird is, as it increase the flight speed, they also tend to decrease the area surface. So we said, could we have drones? But if we want to develop drones that fly, for example, in cities, where sometimes you have these urban canyons where there's strong winds coming, you may want to close your wings, but that's the angle, you want to spread them out. And so we said, could we have drones that can change their morphology to adapt to different types of wind conditions? And again, we look at birds, and we see that feathers are very interesting because you can easily fold them and change effectively the area of the drone. I'll let this play this video that explains how this works. So we can have symmetric folding, so we can change the total surface of the wings to fly at different wind speeds more efficiently. So we tested all of this in wind tunnel, of course. And then we can also do asymmetric folding for rolling. So instead of using elevons, additional elevons to control the roll, we just asymmetrically switch the morphology, change the morphology of the wings, and we can smoothly control this drone in the air. The biggest challenge of this project was to design these feathers. And one of the things, and that's something I'd be very much interested to talk to Sarah, is how could we do local sensing at the level of the feathers of local turbulences, because we know birds do have lots of information coming locally that would allow the system to adapt the morphology without going through a central processing system. At the moment, this drone is teleoperated, and now we have a project where we are extending this feather structure and this agility of the drone to the softness also of the body and adding control. So that's what we're working on. Now, drones have another big problem, and that's size. Because of the laws of physics of aerodynamics, the lift of a drone is proportional to the product of two things. One is the aerial surface, and the second is the speed of the air over this aerial surface. And so in order to increase the lift, you can either fly faster, or you can increase the size of your propellers or wings. And because you cannot fly these small drones much faster than a certain speed, most of the time, if you want to carry larger loads, you have larger propellers or you have larger wings. And then you have a problem of transporting the drone to the location. And most of the companies that make, this is like my former company, they make foldable drones that you can put in a box, then you can assemble together, and then you can fly them out. DJI makes drones that can fold mechanically. You can fold them; they are still in place. And so again, we said, okay, how could we have a drone that can be easily transported in a small package, and then you can simply launch it in the air, it opens up and flies? we went back to nature, and we've seen that insects do indeed, many insects have foldable wings. They keep in the back, like this coleoptera, and they very rapidly deploy them to fly off. If there is a predator, or if they want to go out, they quickly deploy them. They are slower to fold them, but they deploy very quickly. So the surface reduction is up to 10 times folding ratio, 20 to 200 milliseconds deployment time, collision and crash resilient for the reasons that I mentioned before, and very small weight. And so we said, okay, then let's start building drones that have these properties. And of course, we didn't copy exactly the wings, but we started to have developed foldable quadcopters where the arms are like origami structures. They can fold into direction like this, and then they can fold on top like that. The folding in this direction along the red line is used for ensuring the rigidity of the arm during flight. In order to fold them around the body, you have to first open up the top part, and then you can fold like this. And so the drone starts in that configuration. It's a very small package. What we do is that in order to automatically open it, we rotate all the propellers on the same side, which would generate an opening. But like this, you cannot fly. In order to fly, you have to have the two propellers on the two sides rotating in a different direction. So as soon as the drone opens, then there is the top part will fold on top of it, and then there is a magnet with a switch that would detect that the arms are locked in place, and then automatically the two of the propellers would rotate back in the different direction. And so you can see now the system operation here. You can just launch it. Yeah.
It can fold and unfold.
Yeah, maybe. So I just want to show to you in short motion, slow motion in a moment. So it's very compact, you will see. Okay. So there we go. So okay. So essentially, it's like I call it a pocket drone. Let's see. Yeah. You see the folding, then the top part goes in place, snaps in place, and the propellers then switch the rotation. There you go. So if you look in slow motion, it opens, the arms lock, and the drone flies off. Then we made another version, which is this time we tested in the field. It's a pocket camera. It's like some camera that you can keep in your pocket like this. It has visual and thermal spectrum, 5 minutes autonomy, 45 grams. This time the design is slightly different than the previous one, but essentially the idea is the same. So you have this drone that starts in a folded configuration, and then it rotates propeller in the same direction. It unfolds. As soon as we detect the maximum folding, two propellers rotate in different direction, it flies off. It's also crash resilient because of this folding. You see, on the right you have a non-foldable version. On the left you have the foldable version. And because of this energy absorption, this drone can fall on the ground without breaking. This is we tested this with rescuers in a field we call it a disaster village that we have near Geneva. And so you see a rescuer using this drone to monitor a building up in the air. So now, can we generalize this folding structure to fixed-wing drones? Yes, we can. And then what we looked again, we went back to Coleoptera. We looked at the crease patterns that they have, and essentially the way in which these Coleoptera unfold their wings is through two mechanisms. One is like one of these fans, folding fans, for the air, which is closer to the wings, the attachment of the wings. And the other one is a different type of crease pattern at the tips of the wings, which is used essentially for folding upwards the wings. It's much better if you see the animation. So we replicated that folding, these two folding mechanisms that are outlined in those two boxes, the red and the green boxes, and we created a foldable wing, which you see in this robot. So this is a fixed-wing drone which uses these crease patterns inspired by Coleoptera wings. The folding ratio of our drone is 3.8, and the wingspan folding is 2.2. You see that we are slowing down the deployment. It's one of the few videos where we are slowing down the video because it's very fast opening. As soon as you open it, then the wings pop up in place. See that there they go. And then once they're in place, they're very stable and rigid. You can simply launch it in the air and fly off. Now I want to move on to another topic. Do I have to finish at sharp? Okay, so I lost a bit of time. So, but now people talk about drone delivery everywhere. So drone delivery is going to be the next killer application if the regulations are going to be put in place that we can fly these systems around. And you have different companies, it's a bit outdated slide, but many different companies doing experimental flights around. But all these companies, what they are doing is they're always thinking of, because of the law of physics, if you want to transport a parcel of a certain weight or mass, you end up with a large quadcopter. And these are dangerous if they get close to people. So most of these companies are doing what we call business-to-business service. So they are essentially using these drones to go from one logistic area to another logistic area where they land. They have very well-equipped infrastructure where they land, and only trained people can access and load and unload these drones. For the people who think of doing sandwich or drone delivery or pizza delivery, essentially the few operations that they drop the packet or they let it unroll through a cable, for example. They don't let the drone go close to you. But if you're talking about delivery, you know, delivery is like last centimeter. The post officer comes and gives a parcel to you. Could we have drones that go to your hand, and it's like what I call last centimeter delivery? And so there you have two problems to solve. One problem is the safety of the persons that are getting these drones. The second problem is that, you know, there may be collision on the road. The third problem is that imagine that you have a postal service with all these drones that are safe, that are collision resilient. But in order to transport a small book, you have a drone that's big like this. Where do you put all these drones? You have to, so where do you store them in the logistic place or in the postal office? So you have also a size problem. So we designed a new drone that tries to solve all these problems at once.
Probably the next big use of drones is delivery. However, because of the laws of physics, the heavier the parcel is, the larger the drone must be. And this creates two problems. The first problem is that it is very hard to store these very large drones to transport them. The second problem is because of the large propellers, they become very dangerous for people. So with this new drone, we have solved these two problems at the same time. Here, this new concept, the drone becomes the package. When the package is folded, it's very small and you can transport it. When the package is unfolded around the parcel, it provides protection for the people, so that they'll get cut, and it also provides protection for the parcel.
The challenge to design this drone was to integrate everything together.
Yep.
Drone,
so because of sake of time, I move on. So we have this drone. It's a safe drone. We also did a lot of work on the software. So we have an app which is like Uber, essentially. You download this app. If you want to get delivery from people, you say, hey, I want to have this from you. It's or like WhatsApp. For me, it's more like the WhatsApp thing. So you have a list of contacts with people that have different things. You know, they have drones at home, ideally. And you say, hey, Jeff, can you send me the plug for this, the replacement plug? And then the drone, you say, okay, yes, here it is. And then you would put it inside there, close the drone flies off, gets to you, and you see the drone come. So we developed the app. We did we delivered 3D printed parts on the PFL campus over the summer last year. We did 150 deliveries, and it was extremely successful. So now we are spinning off a new company for micro deliveries, last centimeter. We'll see how it goes, but it's going to be fun. Okay, now a few more. So the way in which these drones, these animals move and change their shape is through muscles they have in their bodies. So, and could we have drones that are very flexible, pushable, and still they don't use servo motors, which are rigid, bulky parts? Could we have like artificial muscles in there? And so we looked at, with my colleague Herb Shah, we looked at the electric elastomers, which essentially apply voltage onto parts, and then this contracts and expands. And we looked at the way in which all animals have their muscles. They have a skeletal structure, and then they have agonistic and antagonistic muscles that pull and push this structure. So we created this sort of artificial muscles that by applying differentially voltage on one side or the other side of the structure, you can bend in one direction or in the other direction. And to start with, we didn't make a fully foldable wing, but we started to consider whether this technology could be used for the control of the ailerons. Instead of using servo motors for controlling the ailerons of these drones, we looked at whether we could use these artificial muscles. And the beauty of these artificial muscles is that they are very flexible. You can fold them, you can hit them, they will not break. So here is the drone on the back. Instead of the conventional ailerons with the servo motors, we have two sets of artificial muscles. As you can see, they are passively compliant. So you see that how they are built there. We apply voltage in one direction, they bend in one direction, voltage the other direction, they bend in the other direction. You hit them, they absorb the collision. So they are completely foldable. And so we're talking about 3,000 volts, but the very small amperes. So the total current is very small. You just need to have appropriate converters, and now we have over the past 3-4 years we have very small converters. Yeah, so it's quite great. So very precise. So that's a very interesting thing. We are also developing grippers with electroadhesive properties out of this, which could be carried on drones. But if I have a few minutes, this is the movie The Dream, so the Terminator Dream. So you have all these different types of particles and soft stuff that then becomes rigid, and when it's needed and where it's needed, and you have a machine that can do stuff. Because soft robots are great, but sometimes in order to do work, for example, move a screwdriver, grab stuff, sustain your own weight, you need to become rigid in some parts. And so we said, okay, could we have technology? So variable stiffness, I think, is one of the main challenges of soft robotics, structures that can change stiffness. And so to make a long story short, we devised variable stiffness fibers. These essentially are, let me show it to you in the video. This is a video that explains it. That can change their stiffness.
Which normally is rigid, but when you apply small voltage, it becomes something like spaghetti. But on top of that, it's also very stretchable. It can stretch up to 4 times. And the transition between rigid and soft takes only 10 seconds.
Oh.
Metal core that is encapsulated with silicone pipe. Right now it's rigid. When we heat it up, the metallic core will melt, and the mechanical properties of the whole thread will be those of the encapsulation layer.
Since it is a thread, you can wrap it around objects, you can knit it, you can give all sorts of shapes. And therefore it has a lot of different applications. For example, you can use it for robots that change their shape. You can use it for prosthetic devices. You can use it for furniture that can change their shape. You can use it in prosthetic devices, or you can use it even in medical devices because it is very thin and you can couple it with different technologies in endoscopes, for example.
It shows remarkable self-healing capabilities. We would like to transform our thread in a robotic material that is able to mimic the complex functionalities of biologic tissues.
And so what you see here now for drones is that we can change the morphology of the drone as soon as we heat a little bit of material, which is essentially forming the arms of this drone. We can translate from a drone shape to a car shape. And I want to show this to you. So here it flies. Here it's in flight mode, very stable. And then as soon as you go to the ground, you can shape it now manually into a different shape, and then you can have something like a car. So the propellers can fold, and their propellers are folded, and then you can simply drive around. So this is, and then it's completely collapsible, so you can put it in a pocket. So this is work in progress. Okay, so the title of my talk should have really been biologically inspired soft drones, because that's a type of solution or type of strategy that is widely used in nature. You can use these soft robotics technologies for novel types of adaptive sensors that can bend. You can have mechanical resilience to collisions and safety for humans. You can have adaptive morphologies for optimal multimodal locomotions in different situations. You can have foldability for transportation or rapid deployment, robust and foldable artificial muscles, and even variable stiffness bodies. So it's a great area of research, and thank you very much for your attention.
We have time for a few questions. Please. John.
I have 3 questions.
Okay, so yeah, there are many. Okay, very important questions. Let me start. The first question is about the energy. Are you referring to a particular type of drone or? Yeah. Yes. Okay. So we are using lithium polymer batteries, and so for that we have models. There are no models out there in the literature. We published a paper with our model. It's essentially a computational procedure for given a certain mass of your drone and given a certain type of motor and propeller size that you have, it gives you the optimal battery because the battery will have a weight that you can add. And so we have a recursive model that tells you this is the battery that you have. So there is a very interesting relationship. Typically, you have between, in the less than a kilogram, you have approximately 10 to 15 minutes maximum endurance if you have optimized the system quite well. Now, for the professional ones, like the fixed-wing drones, you can go up to 40 minutes perhaps, but in perfect absence of wind conditions. So yes, that energy is indeed a problem. And the second question was. Yes.
Okay, you can extract the data, but then in order to have the perception of sense, you need to compute. So what's the computation side of the story? Because we know you're not going to compute all the data at all the resolution. You're going to do something very clever.
Yeah. Yeah.
Even have cameras that can use from the car or from the that you look at the edges that they show up only when you move and something.
Exactly.
That is part of the story.
Okay, so the computation is super simple, and the reason why we go for those compound eyes is because they simplify the computation. A lot of the motion extraction, so the optic flow computation comes out directly of the neuromorphic chips, because the neuromorphic chips are sensitive to moving contrast. If there is no moving contrast, they give a zero signal, essentially. They are analog, it's analog VLSI. It's a analog VLSI true. It's a design patented by Toby Delbrook from Caltech. But it is an analog. It's an analog VLSI. Yeah. So we get an. So we get. So the power issue is, it's very interesting that you're saying, because it looks like the power, I'm not an expert in neuromorphic chips, so that design was done by, in Marseille, on the design of Toby Delbrook from, but, exactly, so that's Carver-Mead design, yes. Okay. No, this is not, this is analog. This is analog. Yes, so it's, I can send you the PNAS paper where we published that. Yes, okay, that's an. Now, so the computation is essentially we have a library of filters. So we took all optic flow detection systems, not all, but most of the categories. We put them on the website of this project, curvebase.org, and we made a front end compatible with the output of the signal. So if your choice which type of optic flow detector you want. For the purpose of our computation, what we use is a neural network, not a neuromorph, a neural network that has a few neurons that have a few neurons which are sensitive to pattern of displacement on the vertical line or on the horizontal line, just like the two kernels that I've shown earlier in the presentation. You came in later, maybe. I'm sure if you've seen. So essentially, there are two neurons that do a summation of the signals they see from different optic flow receptors, and then we have a weighting that depends on the polar coordinates of the viewing angle of the photoreceptor. So it's super simple. It's two lines of codes with a sum of weighted inputs, because the inputs already give you the signal. Yes. Yes.
So the philosophy here seems to be, in the words of some other biology types, that one of trading off algebra for computation against the geometry of matched filters. Right?
Yes.
Yeah.
Yes, in essentially, exactly. And another way in which we call this is called morphological computation. So we use morphology for simplifying the computation, because that's exactly what we do. Yes. And then you had the third question or remark that was about the bubbles. Yes. I see.
The insects you describe, they combine many of the things you describe so they can accept it. And that's the reason they do it. They unfold the wings inside, they use their feet to grab and things like that. Can this be done here? Or if you like, the real question for me is, if you have certain requirements for the mission of the can you compare the different designs and figure out the best?
Yes. Okay, so essentially the question is, you're saying, what you're telling me, look, if this design you have shown is not comparable to what insects can do, because yeah, so you're referring particularly to this gimbal, the cage stuff, yes. Now there you can, yeah, yes, 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 yes. So the problem we wanted to solve there is simply the absorption of the collision without the falling ground. So that platform you cannot do anything else than sensing. There are a lot of interesting things you can do with sensing, but sure. Yeah.
What is the beauty side? Can you make these things so that they're durable? And how many of the hits they can sustain in the function? The manufacturing part of this beautiful design. So,
yes.
Can you go into that? How many?
So.
How many times they can operate? How many times they can keep it?
Yes. 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 So all the time we do the characterizations. So in the papers we show what the resistance. Yeah, so there are two things. When we are talking about, if you're talking about for example, the product version of the gimbal robot, they had to change the design because they wanted to ensure that the usability of this, once you shell a few tens of thousands of US dollars for doing that. Okay. So yeah, so they spent, before they made the product, they spent considerable time to improve the joints, so that they don't break. So you cannot simply 3D print them as we did out in the lab. And then the carbon rods, you cannot use carbon rods because if there is a break and they break, first they break at some point, and second they're very dangerous because a person could get cut. So there was a lot of process with the patented process for improving the aspect. When it comes instead to the more experimental type of things like the foldable wings, we have the characterization of the technology that shows how many folding you can have, how many collisions you can have in the paper. After some time, for example, some of these elastomers which are sandwiched between the two rigid plaques, they lose their properties. So it's still very experimental. Yeah.
Quick question. Very interesting talk. I noticed the one thing about all of your absorption, all this stuff. The one critical component that I'm looking at saying is your point of failure is propeller. Do you have any thoughts on making that flexible, soft, durable? I know you trade efficiency for that capability,
yes.
But
yep.
If you hit a wall and you snap a propeller.
Yes. So the question is have you thought of anything about making the propeller more resilient to collisions? And because that's a failure point. Yes, we looked into that and we haven't found any solution because any small asperity or variability in the rigidity of the propellers reflects so badly on the efficiency of the platform. And with those type of small autonomies that we have, well, essentially we cannot. Even if we could control the platform, it would not be efficient at all. So I agree with you, that's a little bit of a problem. You may use flapping wings, which are much more resilient, but they don't scale up well in terms of autonomy with the technology that we have today. And that's why I stay away from flapping wings. There are colleagues who do a great job. Wood is one of those at a small scale. I know they're scaling up a little bit, but yeah, I use propellers and I look at adaptive morphologies of these wings, but propellers are a point of failure. I agree. You can cage them. That's what we are doing now. We're looking at cages around propellers. You lose some efficiency, but
well,
yeah. There was one more.
So you mentioned like your foldable wings where you can fold one side versus the other and segment part of the wing. And you said that with more control or like more sensing on the actual like the feathers of your wings, you would be able to control your robot more efficiently or do more complicated maneuvers. So are you like physically segmenting like each part of the wing, or it looked like you were like holding, collapsing the wing?
So at the moment we are simply collapsing the entire wing. We have a very simple servo motors that tells how much the wing folds in place. So that's what essentially we're just folding in place. Now imagine, so now we are making this feather structure much more extensive than it is in here, also on the tail. And now if you could sense local like stalling positions, you could drive the system into conditions that normally would not do it because it's very difficult to then recover it before it falls. So ideally, I would like to have the control fully on board, decentralized, with local sensing of flexions. We know that birds have mechanosensors at the attachment points of some of the feathers. Many feathers are just here on the tip, and they are simply used to detect when the flow detaches from the wing, which signals a stalling situation. I'm very interested in really having a giant flight. So you go, you stop in the air, you fall, then you fall, you go through a hole, then you gain speed again. So that's where we are going towards with this type of project.
Well, that's time for speaker one more time.
Thank you.